Hello students, you all are warmly welcome to our YouTube channel Chemistry Teacher. Here in this we are going to present you another lesson belong to organic chemistry. So we are going to talk about the isomerism. Isomerism, we found it out what is isomerism in our earlier video. Hope you could remember. Students, we found that out various different representations being for one particular compounds, as it's possible you to have empirical formula, molecular formula, unit structure, we call it structural formula, then it's the shape or three-dimensional structure of the molecule. So there are various different representations. Then students, having of different compounds standing for the same molecular formula. Again, having of different compounds, therefore different structures that you have representing the same molecular formula is called the isomerism. We found that out in our earlier lesson. Then further, we categorize this topic. Isomerism means having of different compounds, different structures standing for the same molecular formula into two types. One was it was having of different structures through having of different structural formulae. We called constitutional isomerism or structural isomerism. It was one type that we talked earlier about. Then we found the other type was the stereoisomerism. Though they have the same molecular formula as well as same structural formula, they have different spatial arrangements. So it's what we call the stereoisomerism or three-dimensional isomerism. Again, you have this topic isomerism being categorized into two different types. So one is constitutional isomerism. It's the having of different compounds, different structures for the same molecular formula through having of different structural formulae. So then the other type is the stereoisomerism. It's having of different structures, different molecules, different compounds for the same molecular formula, though they have the same structural formula as well, having different spatial arrangements. There are two types under stereoisomerism. You could further categorize them into what are those two types. So those two types are optical isomerism and geometrical isomerism. Students, we are going to find them out. What are optical and geometrical isomerism soon. But our first effort here is what are the three types under constitutional isomerism. There are three categories, subcategories you could find under this category, constitutional isomerism. Again, isomerism you could categorize into two types as constitutional and stereo. Under constitutional, you have three categories. One is called the chain isomerism. Let's find that out first. It is chain isomerism. What's the chain isomerism? Students, you have a carbon chain. Main carbon chain, let's say, within an organic compound. When you consider organic compound, there would be a carbon chain representing the main chain, mother chain. So if you change the length of this main carbon chain, and if you remove some carbon from some positions and if you fix them at some other positions on other carbons, you would get these type of isomers. Then it's actually you just play with those molecular formula as well as structural formula given. In real, when you try out drawing of such a structural formula, in real you would get a substance standing for that that structural formula you have drawn. That's the case. That's the thing. If you have real compounds standing for same molecular formula having different lengths of their carbon chain. Okay, let's find it out some examples. Students, it's when you have C4H10, its unsaturation number U is 1. U is the unsaturation number, is the number of carbons and cyclic structures. So, it's you could find it out in the way that you multiply the number of carbon by 2, add 2 on that, you subtract the number of hydrogens on that as well as number of halogens if you have. Then you add the number of nitrogen atoms there. Then you divide that by 2. So you get the number of carbons and cyclic structures. So when you do that on this, it's 2 into 4 is 8 plus 2 is 10 minus 10 is 0 divided by 2 is 0. If you do not have any pi-bond, double, triple bonds. Okay. Then students, it's a carbon chain with single carbon-carbon bonds. So it's an alkane. So I could give you this structure. It's actually this structural formula representing this molecular formula. It's one compound. When you consider this structural formula, there would be a structure standing for that. Okay. Then students, further, I could reduce one carbon. So I could bring that reduced carbon here on the second carbon. If I bring that on the first carbon, it would again become the same linear chain with 4 carbons. Therefore, I am not doing such. So this is a different structural formula than this. It's therefore you have these two structural formula representing the same molecular formula. That's how. So that's how you get chain isomerism. So it's a subcategory of constitutional isomerism because you have different structural formula, therefore different structures. So let me explain another example. Students, let's go to another compound. Let's talk about another alkane. It's C5H12. When you check again for U, its unsaturation number 5 into 2 is 10 plus 2 is 12 minus 12 is 1. It's 0 divided by 2 is 0. So then its unsaturation number is 0. You do not have pi bonds there or cyclic structures there. Then students, I could draw a linear carbon chain with 5 carbons. It's an alkane then with 5 carbon. It's a pentane. The alkane you have here is called pentane. Then students, I could reduce the number of carbon by 1. What then it could be? 1, 2, 3, 4 carbons. So the reduced carbon I can't bring on first carbon. Then again it would be the same chain as of this. I could bring it there as a methyl group. Okay, then others I could write as these. So then it's isopentane or 2-methyl-butane. It's another different structural formula you get. Then students, I could reduce another carbon. So reducing another carbon, I would reduce the carbon number to 3. Those 2 reduced carbon could be brought on the second carbon. So students, what I would get next is this. This is called neopentane in application. It's the trivial name. The IUPAC way you could name it is 2,2-dimethyl-propane. Okay, so for the same molecular formula C5H12, if we first found out what's the unsaturation number, to make that sure we are not trying for any wrong type, means any substance with carbon-carbon double or triple bond. it has to match with the unsaturation number. You need to draw according to the relevant unsaturation number. That's why we first check for the unsaturation number. Anyway, after doing that, satisfying that unsaturation number we have got. So I'm drawing one chain with 5 carbon is the longest carbon chain. Next, what I have done is trying for checking whether there is any other possible structure. What I have done was I have reduced one carbon and brought it on second carbon. So then I have drawn another one. So it is a different compound, and its structural formula also is a different one. Next, what I have done is here is I have reduced another carbon to get another different structural formula. Therefore, it's another structure possible. In that manner, if you change the length of main carbon chain, you could have various different molecular structural formulas standing for the same molecular formula. Through having different structural formula, you would get different structures. If the structural formula is different, it's obvious the structure is different. This way, if you get your isomers, we call it chain isomers or chain isomerism. That's one type belong to the constitutional isomerism. Then students, it's under structural isomerism or constitutional isomerism. We had 3 types. One was the chain isomerism, the other is the position isomerism. Let me explain you what this position isomerism is. Okay, students, now we are going to find out what is position isomerism is. Okay. So by the name itself, it's having different position within the main chain. Different position of what? It could be either different position of the main functional group or a sub-functional group or a branch alkyl group. Such. Okay, let me explain that further. Students, I am going to now show you this one, C3H7Br. So when you check for the unsaturation number, it's having one halogen atom as well. Unsaturation number, 3 into 2 is 6 plus 2 is 8 minus 7 is what? 1 minus 1 is 0 divided by 2 is 0. What I am telling now is U equals 2 into carbon number plus 2 minus hydrogen number minus halogen atoms number plus nitrogen atoms number. So it's divided by 2. That's what I'm using. It's the way I get the unsaturation number just following the molecular formula. Okay. So anyway, the unsaturation number here is 0. Therefore, you don't have, this compound doesn't deserve any double triple bonds. Okay, or cyclic structures as well. Any cyclic structure takes the unsaturation number 1. That's why I'm telling no cyclic structures as well. Okay. Then students, I'm ready to go ahead. When I try for drawing for this molecular formula, drawing some isomeric structures, it's firstly 3 carbons. I would keep that bromine on the very first carbon. So this is one structural formula. Therefore, it is having one structure there. So students, secondly, I could draw the same carbon chain, but change the position of bromine. This is a different one than earlier. Here you have the bromine on the very first carbon. Here you have bromine on second carbon. This compound's name is 1-bromopropane. This is 2-bromopropane. So changing the position of a subfunctional group or main functional group or a branch chain methyl group or such. You could draw such different structural formulae, therefore different structures. That way of having isomers is referred as the position isomerism. Then students, what do we have for the third? It's the functional group isomerism. So let me explain you what functional group isomerism is. So functional group isomerism, by the meaning itself, the name itself, students, it's you are going to have a different functional group now. So it's here functional group isomerism, that what we are having. So students, it's you would get the same molecule formula and you would get different structural formulae through having different functional groups. Let's find it out. So if I give you this molecular formula C2H6O, so if you go through, if you refer this, its students, when you have its unsaturated, when you check for its unsaturation number, it is 2 into 2 is 4 plus 2 is 6 minus 6 is 0 divided by 2 is 0. It does not have any double or triple bonds or any cyclic structure. Its unsaturation number is 0. That's why. Then when you check for possible compounds standing for this is, students, when you have a substance, organic substance, being possible to draw with one oxygen, if you do not find any unsaturation number standing there for that particular one, then with one oxygen, its alcohols, they do not take any unsaturation number, as well as its ethers. Alcohols and ethers are the possible functional groups without taking any unsaturation number. But if you find your oxygen with the unsaturation number 1, then students, it's possible an aldehyde as well as a ketone when you have 1, the unsaturation number being. Okay, so here you do not have any unsaturation number, it means 0. Therefore, it could be an alcohol. It is the well-known alcohol, right? It's ethanol. So students, I could draw an ether as well. So this kind of compounds are referred as ethers. When you have two alkyl groups at two sides of oxygen with single bonds, then you could have ethanol and this is methyl, dimethyl ether are the two possible compounds standing for this molecular formula having different structural formula, having different functional groups. Such an isomerism is referred as the functional group isomerism. Okay, this is the functional group isomerism. So that's the idea of the constitutional isomerism. There are 3 types. One is the chain isomerism, the other one is the position isomerism, the last one is the functional group isomerism. Students, we have another 2 types under stereo isomerism as well. What are those 2 types? As I have already named at the very beginning, students, it's under stereo isomerism, you would find one type being named as optical isomerism. So, what are optical isomerism? I would explain what are optical. Optical means it's light related. So why is that we call it light related? Optical later on, not at the very beginning. So students, it's when you find an organic substance, or when you find let's say a carbon there within an organic substance having 4 bonds around it, means 4 single bonds around it. So then let's say it's not just a structure, just a compound of it. Let's say it's a structural formula. When you are drawing for a molecular formula, when you are drawing one structural formula having 4 bonds around that carbon, then if that carbon is having 4 different functional groups or 4 different atoms or groups bound to that, I'm just naming it as A, B, D, I'm skipping C, so E. So these I'm just giving for saying they are 4 different students. When you have 4 different groups, they are around one carbon being bound with single bonds. Then the hybridization of this carbon is sp3, as you already know. I guess that you already know that the geometry, electron pair geometry around the carbon with 4 repulsion units is tetrahedral. Therefore, the hybridization is sp3. When you have such a sp3 hybridization being tetrahedral, the shape, main shape, so students, those would arrange in the 3-dimensional space in a way like this. It's Bu gate, let's say. It's Du gate, let's say. It's Eu gate. And it's Au gate. If you have such an arrangement around one carbon, 2 single bonds, 4 different groups. So this is the Lewis structure, or we call it structural formula. This is the structure that we represent the bond angles, bond lengths, right? So it's just to give you the idea how those spread in the 3D space. I have drawn these with just single lines, and this is when you draw it in this manner, it indicates that the group bound to this carbon is this. It's coming out the board. When I indicate this with such a line, dot lines, let's say, so it indicates that if this is the plane of the board, while when E and A groups are indicated or given with straight lines, just lines, then those are going on the board. So this is coming out of the board, and this type are going inside the board. Okay, so in 3-dimensional space, those would arrange tetrahedrally in this manner. But now the matter is, these points, these attachments are 4 different groups with 4 different either atoms or groups. You have got this carbon being bound. Okay, so then this is the structural formula. This kind of carbon is identified as asymmetric carbon. It's we call asymmetric carbon. Another name standing for the same is chiral carbon. Chiral carbon. We call it chiral carbon. Chiral carbon. It's chiral carbon. When you have chiral carbon, chiral center, asymmetric center, so the way they arrange could be either in this way, or there is another different possible way. Students, that way I could get with respect to this in this form. So you assume that this molecule is they are going in front of a mirror or something. So this is the mirror. What it could see is itself. So its image that it could see is something like this. This is inside the board, but now at this side. So this is coming out the board, it is D, and further this is through the board, it's E, and this also is through the board, it's A. So then you would get the mirror image of that. This is one, it's mirror image of this. So these are the two isomers possible. They are not the same molecule. For the reason you can't superimpose them as one upon other. When you check for their arrangement in the three-dimensional space, you would find they are different for the reason one is the mirror image of other, and you can't ever superimpose that. For an example, you could see my left hand and my right hand. Hope you could see, right? So if you have thumb, point finger, mid finger, so those fingers you have, they look like the same, but they are not the same. I feel it like my left hand. This is my right hand. Okay, you would say it is just what I feel only. But students, let's say if I find that mistakenly my hands are removed by an accident, so if someone is fixing my hand at the next time in a surgery at other two sides, I would not be able to work out or do things with my hand. For the reason this is actually my left hand only. Fixing this to the right side, I can't call this right hand. This is the same. This is my right hand. I can't have this there, or I can't fix by the surgery this there as to say it's the right hand. It's quite similar to those mirrors that you find, side mirrors in vehicles. If one side mirror is got damaged, then let's say it's the left side mirror, you get damage there. So you need to buy, mentioning it specifically, only the left side mirror, not the right. If you have mistakenly buy the right side mirror, you would not be able to fix that. So it's then not the driver could see their details, but those pedestrians. Okay, so anyway, you have left side mirror and right side mirror being two different. You can't one superimpose on other, similar to my hand. So this is my left hand, this is my right hand. I can't superimpose this on this. See, these are not overlapping or superimposing one upon another. So, but at a time when this my left hand goes in front of a mirror, it would see this right hand, so as its mirror image. So therefore, students, these are two different in the space, three-dimensional space. Those have got arranged in two different ways. It's similar to this. So when you have four different groups got attached to one same carbon through single bonds, it's tetrahedral they arrange. So then in the three-dimensional space, the way they get arranged would be two different, as one is the mirror image of other. They cannot ever be superimposed. These two isomers we call enantiomers, is the name we give. So normally in common we call them isomers. When it's specifically stereoisomers, and out of stereoisomers, when it's specifically optical isomers. We call these two enantiomers. Then students, do we have any way to name them? Any way to identify them? There is one physical method. That we could distinguish them with an experiment. What is that? Students, let's assume this is a liquid, a colorless liquid. Let's assume this also is a colorless liquid. They quite look like alike, but they are not alike. It's you might have seen identical twins, so it appears like they are the same, but they never would be the same. You might have that experience, or you might have heard of. Though they are twins, though they seem identical, they are not identical. They think differently. They are two different felons in the society. Okay, so then students, I was explaining how we could distinguish them with an experiment. So I will explain this word later on. It's you pass monochromatic plane polarized light. Monochromatic plane polarized light. Polarized light. So you do the same here as well. You pass monochromatic plane polarized light. I will explain later on what is this monochromatic plane polarized light actually is. Then students, when you pass monochromatic plane polarized light through this type, it would rotate the plane in this one direction. Let's say it is in left hand side, or let's say it is counterclockwise. It is not the direction where the indicator of a clock is moving. So then it is opposite direction. We call it anti-clockwise or counterclockwise. So this is going in left hand with, let's say, a theta angle. It's getting deflected. It's changing its direction of going. So monochromatic plane polarized light would be rotated by one type in left direction, left hand side. What would be on other? It also would rotate what? Monochromatic plane polarized light. But not in the same direction, it's in the other direction by the same angle. It's rotating it, this is rotating it in left hand side, this is rotating it in right hand side. So, then, is the way we could distinguish them. Then accordingly, we could name those two types, enantiomers. The enantiomer that it rotates monochromatic plane polarized light in left hand direction is referred as, left in Latin means levo. It's referred as levo type. Oh, we don't call it levo type. We just call it L type. It is the L type. Then this is rotating monochromatic plane polarized light by the same angle, but in right hand direction. So right in Latin means dextro. So we call it not dextro type, D type. Is the way we could identify them differently. So it's a physical method. The physical method is you pass a beam of light beam of its monochromatic plane polarized light. So one type would rotate in left hand direction, other in right hand direction. Accordingly, we call them L type and D type. Other two types, enantiomers, is the way we identify them. Then students, what would happen when you get a mixture of both in 50-50 composition, 50-50%? If you mix them in 1:1 ratio, those two types, then when you try passing monochromatic plane polarized light, it would not be rotated in any direction. It would get just pass straightly. Then such a mixture having both enantiomers in 1:1 ratio is referred as, it does not change the direction of light. monochromatic plane polarized light. So it is identified as a racemic mixture. That's what we call a racemic mixtures. Such mixtures are called racemates. Racemates. Okay. Then students, bit about this monochromatic plane polarized light. When we talk about light is an electromagnetic radiation. Light therefore is having within a range of frequencies, many frequencies possible, many electromagnetic waves being possible. In white light you get major 7 different colors, but many subcolors also you get. When you pass white light through a prism, you get those rainbow colors, all the component colors there. Students, its white light consists of various different frequencies. F1, F2, F3, F4, various different. So if you have a method as to filter one type only, one frequency only, it then would appear in one color. Let's say it's F3 only you block others all. If you filter one type only out of those, it would be appearing in one color. So then one color is chroma. So mono is one. So it is monochromatic. Monochromatic light is the way you could get monochromatic light. Then what's that plane polarized thing or plane polarization? Students, those light waves could come from various different directions at a time. It's if a beam of light is not having all the waves, normally we call it parallel. If all the waves are parallel one to other, then it's traveling in the same direction. But sometimes you could have a beam of light having waves following. It could be either same frequency or different frequency, it doesn't matter. Waves could follow different directions. So different phases they are having at a time. So then if you find a method as just to take waves coming in one direction only, blocking all the others, that's what we call plane polarization. It's then when you find light coming from all around to your eye, and when it is about eye's recognition regarding objects that are responsible for that light, then you would be in trouble. It would be quite kind of tired, your eye would feel. So it's quite hard. That type of vision, seeing things, is quite difficult, hard. So your eye would soon feel tired. But students, when all the lights are coming from one place only, in one direction like this, so it's your eye should not work hard capturing the waves from all around. Therefore, your eye would feel quite relaxed. So then it's better perceiving, means receiving these light that coming parallelly, and it's as a beam with all the waves are parallel to each other, not having following different directions. So if you have such different direction, and if you block others as letting one type only to go through, that's we call plane polarized light. When you do that on monochromatic light, that's what we call monochromatic plane polarized light. The reason why we do use monochromatic plane polarized light is, if you have different frequencies, their angles, they rotate would be different, could be different. And the other thing, if you have different phases, different directions they are traveling, it's you can't give one specific angle only. Therefore, it's better if we have monochromatic plane polarized light sent through those two types of enantiomers. Then we could distinguish one enantiomer type as the L type, other type as the D type. These LD types are very important, plays an important role in the determination of differences there in sugar molecules, as well as proteins. The building units of proteins are amino acids. So in amino acids you have such, we call chiral centers, asymmetric carbons. Therefore, it's possible you will find two different amino acids, but they are carrying the same molecular formula and structural formula as well, but they are two different just because the way they arrange in the space are two different. One could be found as the mirror image of the other. Therefore, students, you would find such situations. Then in biological systems, it's very important. It's very specific. You could find specifically one molecule mostly get involved in those constructing of biosystems or doing various functions in biosystem. It's out of them, one type would be more important. Then it's the other type could be totally opposite in their actions they serve. When one is important to create proteins, the other could be a toxic compound. When one is very efficient in, let's say, regarding sugars, in energy, manufacturing of energy by burning with enzymatic reactions, then the other type would be inert, would not be that efficient or such. So therefore, it's very important, this knowledge regarding that optical activity, or we call it optical isomerism, regarding their possibility of being there as enantiomers. Because it's, for an example, it's mostly for sugar molecules, its L type is playing an important role. When it's about amino acids, it's the D type playing an important role. They are in biosystems. So therefore, this LD chemistry, LD2 type, going to be very important in those biological systems, in those biochemistry, the field of biochemistry. Okay, anyway, those are the optical isomers, we call them enantiomers. The having of two such different structures for the same molecular formula, having the same structural formula as well, but arranging in two different ways, as one is the mirror image of other, we call them enantiomers. That is one type of the stereoisomerism. The type is called optical isomerism. Then students, further regarding the optical isomerism, you just assume that when you have a molecule like this, one is hydrogen, other one is Cl, other one is Br, other one is I. I'm just giving you as an example. So it could be arranging in the three-dimensional space as I, Br, Cl in this manner. So there could be another one, because this is a chiral center, because all four groups are four different. It's with single bonds. You have got those being bound with carbon. So it's tetrahedral, the geometry. So then this would be one enantiomer. The other one would be the mirror image of this. So if I draw the other one, I could draw it in a way like this. the closest one, then next one, you have the other one and this one. These are the two compounds, two enantiomers. So out of them, one would be experimentally only you could find that out. One would be the L type, other would be the D type. Okay. Then students, when you have this kind of structure, so I'll say CH3, CH3. It's around this carbon, you have a H. I'll call this Cl. Then this is H, then Cl. When you have this kind of structural formula, when you find such, then students, around this carbon, you would find that out. It's a hydrogen, methyl and chlorine. This is another different group. Then it's an asymmetric one. It's a chiral center. Therefore, you could keep hope of having two enantiomers due to the arrangement or distribution of these groups around this carbon. When you independently consider this carbon as well, this carbon also is having what? 4 different groups. Those 4 different groups around this carbon you are having are hydrogen, methyl, chlorine and this group, which is different from others. Then in that manner, around this carbon also you have 4 different groups. Therefore, it's possible to arrange those 4 different groups around this carbon in 2 ways. Then you could expect 2 enantiomers standing for this carbon as well. But students, when you have a situation like when this molecule is symmetric within this axis, so it's when you find an axis making the molecule symmetric, those 2 sides are the same. So you would find this ability of them here regarding this asymmetric carbon is you would expect 2 different structures. So regarding this carbon also you could expect 2 other different structures. So it seems like you could keep hope of having 4 different structures. At other times, other contexts, not this, you would expect such. It's when you find more than 1 chiral centers, its number of chiral centers into 2 would be the number of possible structures, compounds that you would have, number of possible enantiomers. But here, in a way like this, when you have your structure being symmetric within an axis, then whole ability of having chiral centers, or let's say ability of having enantiomers, it loses. It loses having that different enantiomers. Therefore, there won't be any enantiomers standing for that, such molecules. Such are referred as mesocompounds or mesocompounds. Okay students, if we have talked about optical isomerism, so and it's under constitutional isomerism, we have found out chain isomerism and position isomerism and functional group isomerism. So under stereo isomerism, we look at the optical isomerism. What it remains is just the geometrical isomerism. So students, is what we are going to look at in our next video. So if we are going to round up here talking about isomerism, giving some clues regarding isomerism, showing what actually these isomerism subcategories are regarding chain, position and functional groups as well as optical isomerism. Students, then with the hope as to meet you in our next video regarding geometrical isomerism, we are going to round up here. Okay, goodbye.